So when you check the lepton number, because it's muon, electron, muon, neutrino, and X is there. So for lepton number, for every lepton, it's 1, and for anti-lepton, it is -1. So here lepton number 1, 1. This also for lepton 1. So you can see this element, this particle X is there. So what should be the lepton number of this element, this particle, so that it should be conserved? On the left hand side, you are getting 1. On the right hand side, you are getting 2 lepton number. So what should be the lepton number of this? So lepton number should be -1. So this particle should have a charge 0, baryon number 0, lepton number -1. So which particle can be here, which follow this all properties? Anti-electron neutrino is having all these properties, that it should have a lepton number -1, and the charge should be 0, the baryon number should be 0. So this particle which is released here is actually anti-electron neutrino. Is it clear, this example?
Yeah.
Now, what are the fundamental forces? There are 4 fundamental forces, which are gravitational, electromagnetic, strong nuclear, and weak nuclear. These are the fundamental forces. Means if you are discussing any force, that will be one of this type: strong nuclear or weak nuclear. So these are the basic or the fundamental forces. Now, what is the origin of these forces and how these forces interact or they exist? First, about the gravitational force. Why the gravitational? What is the unit for the gravitational or origin of a gravitational force? Anything which is having a mass will have a gravitational force, stronger or weaker depending on its mass. But if anything is having a mass, it will always have a gravitational force. Like, for example, even your pen or a pencil is having a gravity, your table is also having a gravity. So these objects are attracting each other. But why you don't feel a movement like a table move toward the pen? Because their mass is comparatively small as compared to like planets, so they have a higher gravity, so their interaction or their effect of the gravity is visible. But anything which is having a mass will have a force between them, and that's a gravitational force, and it is always attractive. The gravitational force can never be repulsive. Whenever two objects are there, the gravitational force will always be attractive force. And gravitational force cannot be shield. Like, what does it mean? Say you have two objects which are separated, they have a gravitational force between them, and they are separated by a distance of 2 meters. And example, this object was experiencing a gravitational force of 100 Newton. So if I place an object between them, another mass, the value of the gravitational force which is experienced by this object A will not change. So means the gravitational force cannot be shielded. Even I have many particles between them, but every time it will experience a 100 Newton force. So gravitational force it's because of the mass, it is always attractive, and its range is infinite. Like you cannot specify it is acting for a short range or long, it is acting for infinite range. And gravitational can be ignored in terms of atomic scale because the mass is very small. Like small particles, you can neglect the gravitational force. So why you can neglect the gravitational force? Because their mass is so like there is up quark and there's a down quark. So I can neglect the gravitational force between them. Why? Because their mass is negligible or very small mass. Same way, we have electromagnetic force, the second kind of force, the force which act between the charge object. Whenever the object's having a charge, but this force can be attractive, it can be repulsive. Gravitational is always attractive, but electromagnetic can be attractive or it can be repulsive. And it is also having an infinite range. And this force can be shielded. Like example, if you have two charges are placed, two positive charges or positive and negative charges. So if I place another charge here, then the force which was originally experienced by the charges will change. But in case of gravitational, the force cannot be shielded. Then we have a nuclear force or a weak nuclear force which act on all particles, both lepton and quarks. Quark experience weak, but leptons, its effect is more visible, and it has a range of 10 exponent minus 17 of a meter. And this force is involved for a beta decay. Same way, we have a strong nuclear force which exists between hadrons. Hadrons are actually mesons and baryons, and it is a very short range which act within the nucleus. So these are the fundamental forces whenever the particles are interacting or whenever objects interact. If there is a force, the force can be any one of this type. It can be gravitational, electromagnetic, weak nuclear, or strong nuclear. Maybe they may have more than two forces, or they may have two forces or more than two. Like example, this is an atom, the nucleus of an atom, and it consists of a proton. For example, two protons are there. So proton consists of up and up, down, down, and here also up, down, down. Proton is having a mass. So if it's having a mass, it will have a gravitational force. They also have a charge, so they will have electromagnetic force. They are also quarks, so they have, and they're within the nucleus or short range, so they also have a strong nuclear force. So three of the forces can exist here at the same time. Which force is stronger than the other? There's a way to calculate, but all these forces can exist at the same time. If it's a strong nuclear, then it is within the nucleus, it's a short range, responsible for holding the particles within the nucleus. But strong nuclear force, it's like a spring holding the two masses. So it can be attractive, it can be repulsive. How? Like example, if you have two masses and you attach with a string or a spring, sorry, and if I pull this spring, what will happen if I try to pull this spring? These masses will come towards the center. But if I try to compress the spring, these masses will go away from the center. So means it can be attractive, it can be repulsive. So strong nuclear force, when the particles are coming closer to each other, it is repulsive. When the particles are going away from each other, it is attractive. Is it clear?
Yes.
This interaction. So Then how the particle interact with each other? Actually, particle exchange bosons. How they apply a force? Like example, how a two masses are applying force. So they're exchanging a particle. We call that as boson. So example, sun is attracting the earth. The gravitational force is there. Earth is attracting the sun as well because of gravitational force. So how they are interacting with each other? So they are exchanging a particle with each other, and this particle is called boson. If the boson is due to gravitational force, what we call that as graviton. This boson is known as graviton, but practical evidence, it is only theoretical particle till now. There is no practical experimental evidence to show that graviton exists. It's just a theory till now. But if charges are interacting, like example, if there is two positive charges or one positive and one negative, so they will attract each other, they will apply force on each other. So how they apply force on each other? So they exchange a particle, and that particle is a photon. So if positive particle transfer that photon and negative particle transfer that photon to positive. So they are exchanging a particle. It's this particle is actually, you can understand like it's how they're interacting with each other by exchanging information or the particle, and that particle is a photon for electromagnetic force. For a weak nuclear, it can be W and Z bosons, or W plus, W minus, so three particles. And for a strong nuclear, the particle which are holding, these particles are called gluon. Like example, up quark and there's up quark. So because these are quarks, so how they're interacting with each other, they're exchanging a particle with each other, and that particle is called gluon. Is it clear? So the force exists between the particles, between the charges, between the masses is due to the exchange of the particle. And if it's a gravitational force, it's a graviton. If electromagnetic force, then photon. If it's a weak nuclear force, it can be WZ boson. And if it's a strong nuclear force, it is gluon. This is how we explain that existence of the force. Other particles like photon, bosons, gluons are discovered, but about the graviton, still it's a theory. Existence of a graviton, practically it's not proved. So copy this part, particle exchange model. So this is a diagram which is representing the interaction of the particle. Like example, you can see here, like showing a particle interaction. Say two electrons are there, like charges, so like charges repel each other. So how they repel each other? So they exchange a particle, and because these particles are for interaction of electromagnetic force repulsion act between them. So how they exchange, how they apply force on each other? By exchanging a particle or a boson known as photon. Same thing, if you have electron neutrino and you have a neutron. So this electron neutrino gives electron, and here basically it's a beta decay, a negative beta decay. So what happened in this negative beta decay? A neutron gives proton, electron, and anti-electron neutrino. Or this can also happen that neutron can interact with electron neutrino, result in a formation of a proton and electron. So what happened? How these particles apply force? So neutrino and neutron scattering. So how they apply force on each other? By exchanging a particle which is known as W positive or weak nuclear particle boson. Same way, this is actually a beta decay. What happened? A neutron breaks into proton, electron, and this will be anti-electron neutrino, not electron neutrino. So that it will exchange another particle which is called boson, which is W negative. And two, like one is up, another one is down. So two quarks are there. Which force interaction is there between them? The force is known as gluon. This is just an idea that you should understand, like interactions and what force exists between the particles. So example, give similarities and difference between particle and antiparticle. So similarities and difference we already discussed in the beginning of this chapter, that similarities, they will have the same mass, they will have the same magnitude of the charge, and differences, they will have opposite charges, they will have opposite spin. The rest mass energy of electron is 0.5 mega electron volt. A photon of energy 1.1 mega electron volt produce an electron and positron pair. Calculate the total kinetic energy. So if there is a photon, this photon produce electron which is having a mass of 0.5 mega electron volt. This is a mass, rest mass, and it produces a positron also with a rest mass of 0.5 mega electron, and the energy of a photon was 1.1. So the question is, what is the kinetic energy of electron and positron? So the total energy minus the energy which is needed to produce these particles, when I subtract them, I will get how much is the kinetic energy. So as you can see, so it's 1.1 is the total energy minus the energy required to produce proton and antiproton, electron and positron. So this result in 0.1 mega electron volt. Then give two differences between hadron and lepton. So what are the differences between hadron and lepton? So you can see, what are hadrons? Hadrons feel strong nuclear. Leptons do not feel. And leptons are fundamental, hadrons are not. Give two examples of baryon. So proton and neutron. Give two differences between baryon and meson. So what are the differences between baryon and meson? Baryon are formed by three quarks. Meson are formed by quark and antiquark. Meson have integer spins, like, but baryons have half spin, like half, but they will have, mesons will have, like example, +1, +2, +3, or -1, -2, -3. Then state the quarks that form proton. So the quark which form proton, so it will be up, down, down. Sorry, up, up, and down. And for neutron, it is up, down, down. For anti, so anti-proton, it will be, all the anti-particles will be there. It will be anti-up, anti-up, and down. And for anti-neutron, it will be anti-up, anti-down, anti-down. Use the conservation law to determine which interactions are possible. So if we check the first interaction, we have to check the charge. A, B, and C are possible, but A is not possible. Why A is not possible? So we have proton gives a neutron plus positron plus anti-electron neutrino. So first I'll check the charge. Charge of proton is plus, neutron is 0, positron is plus, anti-electron neutrino 0. So charge is conserved. Then I will check the baryon number. Baryon number for every baryon is +1. So this is +1. This is +1. Lepton, it's baryon number 0. So baryon number is conserved. Then I'll check the lepton number. Proton is not a lepton, so that's 0. Neutron is not a lepton, 0. For every lepton, like electron, neutrino, tau neutrino, and muon, neutrino, the lepton number is +1. And for anti-lepton, it's -1. And this is also anti-particle -1. So you can see the lepton number is not conserved, so this interaction cannot occur or cannot happen. The remaining two, when you apply the conservation, you will find that it can happen. List 4 fundamental interaction in order of strength. So fundamental interactions: strong nuclear, then electromagnetic, then weak nuclear, and at the last it is gravitational. This is the strength of the interaction. Like strong nuclear having a greater force as compared to electromagnetic, higher than weak, and weak will have higher than gravitational one. Then which of these 4 forces will the following particle feel? Neutrino. Neutrino is a lepton. So leptons, which kind of force? The lepton always experience weak nuclear force. So you can see weak nuclear force. Electron is having a charge also, and it's a lepton, so it is weak nuclear, and it's also having a mass. So weak nuclear, gravitational, and electromagnetic. And proton is having a charge as well. Proton is having a mass as well. Proton consists of quarks, and quarks can experience strong and weak nuclear both. Mostly strong nuclear, but weak nuclear is also there. So all the 4 forces are existing within this. Is it clear? Discussions?
Yeah.
So the other topic, like the past paper discussion, is there, but first I want you to learn all these particles, about the particles, so that in next class we can have or discuss the particle interactions from the past paper questions. Any question related to the class today?
No.
Okay.